Hello and welcome all. Thank you so much for joining us for our last day of the Rich Earth Summit. So great to see so many of you trickling back in here. We have our in-person audience here in Brattleboro, Vermont. And we're going to get started shortly with lots of amazing presentations on technology and agriculture and toilets for the rest of the day. And at the end of the day, we'll have some informal breakout sessions for folks to gather and connect. As we get started, I just want to say a really special thank you to all of the sponsors that help make this event possible. We're really grateful to Wasted, who's here today and will be presenting later today, who is reimagining the portable sanitation industry with an ethos of source separation, modernized logistics, and nutrient recovery. You can also check out a video from them on our virtual exhibits page on the Summit website. We're also grateful for Brightwater Tools, a Summit sponsor, who is a spin-off company of the Rich Earth Institute, developing novel building scale wastewater nutrient recovery systems. And our third sponsor this year is P-Style, which makes stand-to-pee urination devices, which make collecting in a variety of containers accessible to all. Our first panel of the day, which Abe will be moderating, which is going to be on some different treatment technologies and processing research. So we'll shift right on into that. And I'll pass it over to Abe to do our first introduction.
Okay. Thank you, Julia. Yeah, so we're just going to open it right up to a large number of presentations today. I believe it's seven or eight. Yeah, seven. And because it's so long, we're going to have a break in the middle for questions. So you don't have to hold your questions through seven presentations. But please do hold them, or put them in the chat, or jot them down for yourselves. And we'll have questions after the third presentation. So this first one, I'm happy to have Chibambila Simbeye will be presenting. Chibambila Simbeye is a civil engineer master's candidate at the University of Cape Town. He's passionate about sustainable infrastructure and technology that ameliorates the human living experience while supporting circular economies. The insights he presents today stem from his dedicated work as part of his master's research project. So please take it away.
Greetings, everyone. Today, I'll be presenting our work titled Phosphorus Recovery from Source Separated Human Urine as Vivianite. So here's the project team, and I'll get right into it. So phosphorus recovery as Vivianite. Well, Vivianite is a hydrated iron phosphate that appears blue in color when oxidized, and it has various uses, which include it can be used as an iron and phosphorus fertilizer. It can be used in the production of lithium iron phosphate, that's for battery production. And it can also be used as a paint pigment for authorship and time verification due to its slow decay properties. With all this, in its purest form, it's able to draw a market price of about $100 to $500 per kilogram. So what's our theory? Our theory is that if we add iron to salts, to urine, under the right conditions, we can precipitate this valuable Vivianite. So then with that, we set out the following research objectives. The first one was to use thermodynamic models to determine how the yield and the purity of the Vivianite were affected by the type of iron to salt used, the type of urine, the temperature, the pH, and the iron dosage, also referred to as the Fe to P molar ratio. So then the next was to perform experiments using synthetic urine to validate the findings of the model. Following this, we had to perform physical experiments with real urine at the optimal conditions determined previously, and then see how those results compared to what we've done previously. So that's our experimental setup. There's a benchtop experiment. In the center, we have a jacketed reactor vessel that is temperature controlled, and we have pH controls at the same time and a magnetic stirrer to keep the solution homogeneous throughout the experiments. The first set of results, which investigated the influence of the type of iron to salt, shown below. You can see that we use three different types of iron salts: an iron sulfate, an iron chloride, and an iron hydroxide. They're added in different masses. This is because in order to achieve an Fe to P molar ratio of 1.5 from each salt, we need different masses due to the different molar masses. Then if we look at the results of yield and purity, we can see that the curves overlap. This tells us that provided that the Fe to P molar ratio is the same, the type of salt will not affect the yield and the purity of Vivianite. Therefore, the question becomes a question of which is the most economical and easily available. And in our case, we had iron sulfate being that salt. Then the next set of results shows the influence of the type of urine on the vivianite precipitated. And we have 4 types of possible urines. There's acid stabilized, alkali stabilized, fresh urine, and hydrolyzed urine. If we look at the first curve, which is the yield curve, we can see that for the hydrolyzed urine, which is the light blue curve, it has a narrow window within which it yields vivianite. And this is because when the urine is hydrolyzed, you have high carbonate concentrations. And if you add iron into the solution, those carbonates compete with the phosphates in that range, and the solubility tends to favor the precipitation of iron carbonate over that of vivianite. A similar thing happens in the alkali stabilized urine. Because we're adding calcium hydroxide or magnesium hydroxide, there's a high presence of cations, and as the pH increases, those cations tend to compete with the iron for the phosphate, and above a pH of 8.2 to 8.5, the solubility rules favor the precipitation of those other metal phosphates over that of vivianite. Then if we look at the purity, we can see that at the same time, the alkali stabilized was the lowest performing because we did have spontaneous precipitation of gypsum, calcium sulfate. Then at the same time, the hydrolyzed did have high purities, but at the same time, a very narrow range due to the lower yields. So in this case, we discovered that the best performing types of urine were acid stabilized urine and fresh urine. However, if you look at the reagent requirements, so just to extend this graph a bit, it shows the reagents required to first stabilize the urine, treat it, and then restabilize it. So when you see the types of urine, we can see that fresh urine required the least amount of total reagents. And there are 2 columns of fresh urine, because the first one is using the fresh urine and then acid stabilizing. The second one is using the fresh urine and then alkali stabilizing. But overall, we can see that using fresh urine had the least reagent requirements. Therefore, we selected fresh urine for this set of experiments. Then the next factor that was investigated was the temperature and how it affects the yield and the purity. And you can see our temperature bands on both curves span from 20 to 40 degrees. This is because above 40 degrees, you risk the potential of chemical urea hydrolysis and you lose out nitrogen from the stream, which we didn't want. Therefore, we limited our work to that. And if we start from the yield, we can see that regardless of the Fe to P molar ratio, which is the dose, the curve remained constant, meaning that the temperature in that range does not affect the yield of the vivianite. And at the same time, when you look at the purity, we can see that for lower Fe to P molar ratios, there was a reduction in purity. This is because the solubility of vivianite, even though that particular one is not affected, the solubility of other co-precipitates is affected, and they tend to precipitate more when the temperature increases, thus reducing the purity of the precipitated solid. That's over there. And the next factor we looked into was the influence of pH and the ion dose on vivianite precipitation. So we'll start by looking at graph A, which shows the yield. We can see that yield is maximized when the Fe to P molar ratio is equal to or greater than 1.5. Then if we look at the solids produced for an Fe to P molar ratio of 1.2, we can see that as the pH increases, we do have the spontaneous precipitation of hydroxyapatite. That's because there is not enough iron to precipitate out all the phosphate, and then the calcium has a chance to also precipitate that other phosphate. Then at the same time, we do have precipitation of struvite because there's still available calcium to react with the magnesium that's within the urine. Then if we look at the one that's dosed at an Fe to P ratio of 1.51, we do see that there is very minimal spontaneous precipitation. That's because within the pH range of say 4 to 7, the solubility highly favors the precipitation of vivianite, but as the pH starts increasing, you do have slight precipitation of the calcium phosphate, the hydroxyapatite, and then above 8.5, it then rapidly increases because solubility in that range will favor its precipitation. But then if we overdose the urine, that's have an Fe to P ratio of 1.6.1, that's greater than 1.5.1, we do see that there is no precipitation in the range of pH below 8.5. And spontaneous precipitation of hydroxyapatite only happens above a pH of 8.5, where solubility will favor its precipitation over that of vivianite. So then we now had to verify the findings with synthetic urine. And we can see that after performing experiments, there was a high correlation in terms of yield and purity of the results. We then performed XRD tests, and the scans did identify vivianite with the best purities occurring within the pHs of 6 and 7. Then at the lower pH values of 5, we did tend to have noisy scans. That's due to possibly the amorphous nature of the solids. And at the pH of 10, we also tended to have amorphous solids at the same time, possible co-precipitates based on what we know. Then the next step was to perform the experiments with real urine, and the results did not correlate well. However, we can see in the yield that it still shows a trend of increasing yield as pH increases. However, for purity, it tended to be about the same throughout. So then performed the next RD scan, and we noticed that the scans were noisy and inconclusive. We then performed other tests, which is the EDS test. We discovered that there was a high presence of carbon in the solids, and collaborating that with the COD tests, it told us that there are possibly organics present in the solids. And the absence of nitrogen and sulfur within these solids told us that the organics present are not proteins. At the same time, there was no calcium and no magnesium in the solid, which tells us that there were no other co-precipitates of metallic ions. Then we'll look at the Fe to P molar ratios of the solids at the different pH values. They were close to those predicted by the model for vivianite. So we decided to perform like visual scans to see what's going on with the solids. And based on literature, it does tell us that if there are organics present in the solution where vivianite is being precipitated, they tend to attach to growth points, affecting the formation of the crystals, and you might end up having an amorphous solid. So if you look at these two scans, the first scan is from the synthetic vivianite, and the second scan is from the vivianite from the real urine, which tells us that the organics could potentially be affecting the way the vivianite precipitates. And then the next step now was to verify that they're actually organics. So we had to perform an experiment, which is basic incineration at 600 degrees. And if we look at that curve, we can see that the first graph is pure vivianite, representing the vivianite from the synthetic urine. And the following three columns represent the vivianite from the real urine at different pH values. We can see that the vivianite from the real urine consistently lost about 12 to 15% more mass than the vivianite from the synthetic urine, indicating that that extra mass loss was potential organics within the sample. So having done that, we said maybe let's try to purify the sample, and performed an experiment where we washed the sample with deionized water, and we also washed the sample with alcohol to see how any improvements were made. And we had the best results at the pH of 6.0, where we ended up having a yield of about 93%, and the best purity after washing with deionized water of about 79%. So in conclusion, we were able to get urine, add iron to sulfate, heptahydrate, at the particular experimental conditions in terms of Fe to P ratio greater than 1.51, and the pH of 6, like 25 degrees Celsius, and we're able to produce vivianite with a yield of 93% and a purity of 79%. So what's the outlook of our work? Well, the future, we hope in the future, we can focus on implementing such technologies in treatment trains where economically feasible, and maybe developing more innovative products that can help us recover such a valuable resource from urine. Then at the same time, we intend to look into further research, or would recommend further research into improving the purity, because we know that in order for us to extract that high value vivianite or yield its economic potential, it has to be produced in the highest purity. So thank you for listening. If you have any questions, feel free to email me at chibambila@gmail.com, and the work is also available online for you to read further into our methods and more detailed results. And I hope you enjoyed. Thank you.
Okay, so the presentation is by Weonjung Sohn, and Weonjung Sohn is currently a PhD candidate at the University of Technology under University of Technology Sydney at UTS under Professor Hok-Young Shun's supervision. Her main research interests include biological nitrification processes in membrane bioreactors for nutrients recovery in a circular economy from source-separated urine. So this one's also pre-recorded, and Weonjung is not here today, but one of her colleagues is. So if you put comments in the chat, those may be able to be answered anyhow.
Hi everyone, I'm Weonjung Sohn from University of Technology, Sydney, Australia, and I'd like to introduce my research, which is microbial community analysis of a membrane bioreactor incorporated with biofilm carriers and activated carbon for the nitrification of urine. As we already know, with the exponential growth of the global population, the increased demand for food production resulted in higher dependence on synthetic fertilizers. As can be seen in this graph, since 1961, global NPK fertilizer use increased by almost sixfold by 2020. In our current linear economy, the production of synthetic fertilizers contributes around 2% of global energy consumption and also results in large greenhouse gas emissions and depletion of limited resources. In addition, the excessive nutrients discharged into water bodies poses a major global environmental challenge like eutrophication. Given this situation, our urine is like liquid gold because it's rich in essential nutrients for plants, which are nitrogen, phosphorus, and potassium. Although urine accounts only 1 volume percent in the wastewater, it accounts for 80% of nitrogen and 50% of phosphorus and potassium in municipal wastewater. Source separating urine and nutrients recovery as a fertilizer can offset the 13% of global fertilizer consumption. Therefore, by source separating urine and transforming urine into a fertilizer, we can close the loop to make a circular economy. In one of our university buildings, we have sewage pipes which can separate urine from waterless male uriners in every floor. This network allows us to collect the source-separated urine. However, direct use of urine as a fertilizer is very smelly due to volatile ammonia and has unwanted organics and micropollutants. Therefore, urine nitrification in an ultrafiltration membrane bioreactor with activated carbon can be an innovative solution to address these drawbacks. In the bioreactor, ammonia oxidizing bacteria converts ammonia into nitrite, and then nitrite oxidizing bacteria converts nitrite into nitrate, which lowers pH without any chemicals addition. At the same time, high organic contents can be removed and micropollutants can be absorbed onto activated carbon. In addition, by using ultrafiltration membrane, virus and pathogens can be rejected, and finally, nitrogen, phosphorus, and potassium can be recovered in one final product as a liquid fertilizer, achieving a circular economy in nutrients. However, one remaining challenge is a long hydraulic retention time, which makes the system large footprint and more energy consumption. To overcome this challenge, we decided to add biofilm carriers in the MBR, which can reduce HRT by supporting more biomass, especially slow-growing nitrifying bacteria, and this can potentially lead to a compact and high-performance MBR system. So, as my research objectives, I focused on investigating the effects of biofilm carriers and PAC incorporation on the overall performance, including nitrification rate and HRT of MBR, treating source-separated urine compared to the conventional MBR. Moreover, to the best of our knowledge, little attention has been given to the microbial communities in the urine MBR process so far. Thus, I also focused on demonstrating the effects of the incorporation on microbial diversity and composition in achieving efficient MBR performance treating source-separated urine. At the same time, I explored the effects of the incorporation on the abundance and distribution of key functional bacteria, focusing on dominant nitrifying bacteria in both suspended and attached growth forms. This figure is showing the schematic diagram of experimental setup of incorporated MBR, and another conventional MBR was operated in parallel for the comparison study. Both MBRs were fed with hydrolyzed source-separated urine after the proper startup phase with diluted urine feeding and operated by pH-based feeding mode. For biofilm carriers, round and parabolic-shaped biofilm carriers were added with 5 volume%, as its shape and low depth can prevent biomass clogging and also transfer of both nutrients and oxygen. For the microbial community analysis, suspended sludge from both reactors as well as attached biomass on the biofilm carriers were collected at the end of the operation, while seed sludge was sampled before seeding into each reactor. The samples were then sent to the UTS Next Generation Sequencing Facility for DNA extraction and amplicon sequencing. As a result, the incorporated MBR showed significantly higher nitrification rate by 36% compared to the conventional MBR, and the following HRT was reduced by 40% from 10 days to 6 days. In addition, the removal rate of total organic carbon increased by 11% from 85% to 96%. As a result of microbial analysis, this table 2 is showing the sequencing depth and observed operational taxonomic units, OTUs, along with the diversity estimator as Shannon index for each sample. Rare fraction curves were also generated based on the observed OTUs to examine the difference in microbial richness. The diversity and richness were highest in the seed sludge, and then reduced by transition feed water to source-separated urine in the conventional MBR. However, in the MBR with the incorporation of PAC and biofilm carriers, even lower diversity and richness were observed. This result might be because the addition of PAC and biofilm carriers was able to create a selective force that enriched certain species, making them predominant microbes in the system. Further taxonomic analysis down to phyla and genus level was conducted for more thorough and detailed information on the bacterial communities. As a result, the feed water change to source-separated urine significantly shifted the dominant sequence order from the seed sludge. Interestingly, PAC addition did not change the order of dominance among microbial phyla. However, it resulted in an increase in their abundance by up to 3%. Overall, the incorporation of PAC and biofilm carriers highly enriched the proteobacteria and firmicutes, which explains the better TOC removal rate in the PAC carriers MBR. After that, we had a closer look at the enriched nitrifying bacteria in different growing forms. The acclimation of seed sludge with source-separated urine highly enriched predominant AOB, Nitrosococcaceae, and NOB, Nitrospira, in the suspended sludge by up to 30-fold and 20-fold respectively. The predominant AOB, Nitrosococcaceae, showed 7-fold higher enrichment by attached growth on the biofilm carriers rather than suspended form. Overall, comparing the abundance of nitrifying bacteria between the two reactors, the incorporated MBR significantly enriched the abundance of nitrifying bacteria compared to the conventional MBR. As a conclusion, biofilm carrier and PAC incorporation highly improved nitrification rate and the following HRT and TOC removal as well. A comprehensive analysis of the microbial dynamics in the incorporated MBR demonstrated the abundance and distribution of key functional genera, especially nitrifying bacteria. This enhancement suggests the feasibility of more compact and highly efficient MBR system for source-separated urine nitrification. Finally, I'd like to thank ARC NICE-Hub for supporting my research, and I also thank Professor Ho Kyung-Shon and Dr. Sharp and my research group members. Thank you for listening.
The next session will be from Natnael Demissie, who is a member of the Swedish University of Agricultural Sciences and Addis Ababa University Institute of Biotechnology. And if you can share your screen, we'll let you know if it comes through.
Oh, no.
There we go. Yes, that looks great. Okay, thank you. Go ahead.
Hello and welcome everyone. So today I'll be presenting our research entitled with photoinactivation of Jacobin urease in fresh urine using dichromatic UV lamp. So go directly to the contents. And as all of you are familiar with the urine, it represents 1% of the volumetric load of the household wastewater. However, it contains most of the nutrients required to grow the plants. Therefore, so separating of urine could help recovering these valuable nutrients in addition to reducing the nutrient load to wastewater treatment plants. However, large-scale separation of urine in urban setting and then applying them in agriculture faces a logistical challenge, which necessitates a way to concentrate these nutrients in one form or another. And to concentrate the nutrients in the urine must be stored and then concentrated on sites or transported to centralized system. And in doing so, some nutrients like nitrogen and phosphorus are lost in collection pipes and storage tanks due to hydrolysis of urea by urease enzyme, which leads to formation of ammonium salts like struvites and calcium phosphates that are normally trapped as scale in pipes or storage tanks. So for technologies aiming at recovering the nitrogen in the form of urea, stabilization is required before concentrating the urine. And conventional stabilization methods applied in source separated urine employ chemical additions such as acid addition and alkaline additions. And these additions may not be safe or convenient. So an alternative chemical-free stabilization method is required. And to this end, we propose UV treatment, which we know mostly applied for disinfection purpose in drinking water treatment plants. And this UV treatment is previously reported to inactivate urease enzyme by either direct photolysis or photooxidation, since this urease contains amino acid residues like cysteine, histidine, and tryptophan, which contain photosusceptible functional groups. This UV treatment can affect the functional groups, leading to the inactivation of the enzyme. So in addition to this, in addition to the direct photolysis, which is normally measured by quantum yield, reactive radicals formed during UV treatment, like hydroxyl radical, can affect the enzymatic activity also. So in this study, what we try to fill the gap is what we want to investigate is the inactivation of urease. And previously, it has been done in water and phosphate buffer, but here we wanted to see the inactivation of urease in urine. And we also wanted to answer how much energy is also being taken. And to do this, we followed such a methodology where urine was collected, and then it was pulled and mixed along with urease, and then it is subjected to UV treatment. And after the UV treatment, the urease activity is measured by tracking the conductivity. And as a control, we also included water and synthetic urine to understand how the enzyme is functioning in different matrices. So going to the results. In the UV control systems, urea hydrolysis rates were the same among water and synthetic urine, whereas it was a little bit slower in the fresh urine. And total ammonium nitrogen concentration reached equilibrium concentration within 2 hours for water and synthetic urine, whereas it took almost 4 hours in real fresh urine. The slower enzymatic activity in fresh urine is attributed to factors like presence of heavy metals like cadmium, cobalt, copper, nickels, and zinc, and also factors like thiols and taurines and presence of thiols like taurine and creatinine, because these heavy metals and thiols are previously reported to inhibit the action of urease. And going further to UV treatment of water and synthetic urine, we understood that the UV treatment significantly altered the enzymatic activity, both in water and synthetic urine. And also in the UV treatment of urine, the hydrolysis was halted, but it took more energy. And then during the UV treatment, the rate of enzymatic activity was a bit 50% higher than the UV treatment in the controls, because when we do the experiment, we cannot separate the urea out of the urine. So while we do the experiment, urea was being hydrolyzed in the photoreactor. So to compensate for this loss, we supplemented with urea after the treatment, and then we tracked the conductivity, where we have seen that the enzyme has lost its catalyzing potential. And this can be further discussed by this graph, where we measured the UV absorbance. In these blue and orange lines, you will see the UV absorbance of synthetic urine and also urea. And then after the UV treatment, the absorbance increased like this, if you follow the arrow. And in all of the matrices, the absorbance increases as the wavelength decreases. And also from the previous studies, we know that the photochemical property of urease increases as the wavelength decreases. For example, there is the literature reported in tryptophan quantum yield, which increases by more than 10-fold. And also, this also works for the molar absorption. And at 254 nanometer, the solutions of urea is also transparent, and the urease solution absorbs slightly. And finally, during UV treatment of urine, radicals other than hydroxyl radicals are also formed, like carbonate radicals and sulfate radicals. And then these radicals could also supplement inactivation, because they have comparable reaction rate constant with amino acid residues like tryptophan. And in conclusion, UV treatment can inactivate the urease enzyme in all of the matrices. And in addition, but it took more than 54-fold of higher energy than compared to the synthetic urine. And we understand that this UV treatment could be potentially integrated with nutrient concentrated technologies like urine drying. And previously, we tried the same technology to remove pharmaceuticals, and then we were able to remove more than 50% of the pharmaceuticals from the urine using the same amount of energy. And then I'll share you the link for the article. And thank you for your attention. If you have any question, you can ask me in the chats, or you can also follow our blog using the following link. Thanks so much.
Wonderful. Thank you so much for that presentation. We have one more presentation before we will break for some questions. This one's from Courtney. And Caitlin is an avid P-cycler and a recent PhD graduate from the University of Cape Town. Her research focuses on nutrient recovery from wastewater, non-sewage sanitation, and membrane technologies. Caitlin, are you here and ready to roll?
Hi, I am here and I'm ready to roll.
Great.
Sharing screen. Okay, are we good?
Yes, looks great. Go ahead.
Okay, great. So first, just Thanks to be here. This is my third time presenting at the Rich Earth Summit, and I guess this is the last part of my PhD work. So you guys have seen it all, I guess. So now let's see how we can go next. So this work is based on the following published paper. And just some background. So one of the things we've been focusing on throughout the summit is that the nutrients in urine need to be concentrated if we want to be able to get them to the places where they need to be used. So that has been the major focus of my research. And I think 2 years ago, I presented on how I developed a reverse osmosis treatment process to concentrate the urine. But I'd kind of got stuck at a concentration factor of 2.5. So we said, well, why did that happen? What are the limitations of RO that meant that we couldn't concentrate it even further? And one of the problems is that as the solution becomes more concentrated, the salts that are in your urine begin to precipitate and they'll form on the membrane, which reduces its efficiency. And then the RO systems are just limited by certain operating pressures and design pressures of the membranes. And as the solution becomes more concentrated, you need to apply a higher pressure to overcome the osmotic pressure of the liquid. So that got us thinking, how can we concentrate the urine even further? And one of the things that came to mind was freeze concentration. So the nice thing about freezing is it doesn't scale membranes like with RO, and it uses much less energy than evaporation. And last year, Abe had a great presentation of what they've done using freeze concentration. But what we actually wanted to look at was something similar but slightly different, which is called eutectic freeze crystallization. And it's basically an extension of freeze crystallization, but you recover ice and salts at the same time. So how does it work? Basically, what happens is you have an aqueous salt solution, and in this region, you will have only liquid. And then you have a region where liquid and ice will form, and then another region where liquid and salt would form. And then there's a certain temperature and concentration range where both salt and ice will form. So when you've got your little reactor of urine, as you start cooling the solution, eventually you'll reach a temperature where ice will begin to crystallize. And as you cool it further, more ice begins to form. And the more ice you form, the more concentrated the remaining liquid is. And eventually you reach a point called the eutectic point. And at this point, what happens is salts begin to crystallize at the same time as the ice. And then what you can do is you can switch off the stirrer in your little reactor, and because the ice and the salt have different densities, the ice will float to the top of the reactor and the salts will sink to the bottom, and you can recover them separately. The thing is with this technique, EFC, there's two parts to it. One is it works best on highly concentrated solutions. So that's why pre-concentrating the urine with RO is quite valuable. But the second thing with EFC is the industries that it's typically being researched in at the moment is like mining and textile, and the kind of wastewaters they're dealing with in those situations are, I don't want to say simple, but simple compared to urine. Urine is very complex in terms of all the dissolved salts and organic compounds. So we weren't really sure if EFC was going to even work with real urine. Oh, sorry, some more. There's our ice and our salt. So the objectives of the paper were firstly just to model the system, and then to show experimentally that salt and ice would crystallize simultaneously at eutectic conditions. And then based on those results, do a little bit of a theoretical mass balance for a full-scale system, and then compare the energy requirements for this hybrid RO-EFC system. So the urine is first pre-concentrated with the lab scale RO. Here we just continually recycle the brine and collect the permeate until we've recovered the amount of water that we need to remove. And then for the freezing, so we take our RO brine, and the first stage is just freeze crystallization. So we recover ice and brine, and then we do a second freeze crystallization where we recover more ice and more brine. And then in the third stage, we were able to reach the EFC conditions where we were able to recover the ice, the product, and the salt. And we did it in a little jacketed crystallizer, like you can see in the picture, in a batch mode. So whereas Abe did block freeze concentration, we're doing suspension freeze crystallization. So this time with the RO, we were able to remove a bit more water. We had 70% water removal, and you can see some of the urea and potassium recovery on the screen. And then we took our, this is our model. So after modeling this concentrated RO stream, what we saw is that you had to remove significantly more water before the first salt would form. So you can see here at about minus 10.5 degrees, the model predicted that the first salt would begin to crystallize, and that is sodium sulfate decahydrate. And I think in total, it's about 90% water removal before we reach the eutectic point. So then we went about experimentally seeing if the salt would form, and it would be nice if I could have a picture of the real urine and the ice, but unfortunately you can't see anything because the urine became so dark. But we were able to recover salt at the bottom of the reactor, and we sent that off for analysis using X-ray diffraction. And the sample came back and it said, yes, this is sodium sulfate. The reason it's not sodium sulfate decahydrate is because when you dry the salt, even at room temperature, the waters of hydration evaporate very quickly. So we were able to confirm that you can actually use eutectic freeze crystallization with real urine. And then based on our results, we did a bit of a theoretical mass balance. So you could see that at a 95% water removal from 1,000 kilograms of urine, you would be left with about 47 kilograms of liquid fertilizer. That is 11.5% nitrogen and 3.4% potassium. So I'm sure some of you are wondering, where is the phosphorus? We stabilize our urine with calcium hydroxide, and the phosphorus precipitates in that stage and is recovered separately. But you could very easily mix that back in to increase the phosphorus content. And then at the bottom of our reactor, you would recover about 3.5 kilograms of the sodium sulfate salt, which is actually really great in terms of fertilizer quality, because we know that the high salt concentration in urine isn't exactly ideal in terms of fertilizer use. So then I took a trip down to the local garden center, and I tracked what are niche liquid fertilizers selling for. And we can see that the sales price was directly proportional to the nitrogen content, which was interesting. I then compared the composition of my two fertilizers using just RO and the hybrid RO EFC process to commercially available fertilizers. And I was surprised to see that the RO, which we had quite a low concentration of nitrogen and potassium, actually matched a commercial fertilizer. So if we were to sell these in the store, apologies everyone, I should have converted these to dollars. We could sell the RO one for about 150 Rand per liter. I think that's around $7. And then 450 Rand per liter for the RO EFC. So what's that, $23 approximately. And then I compared the different processes in terms of energy consumption. So if we look at the energy required to treat nitrogen at a wastewater treatment plant and to produce urea synthetically, you can see we're around 18 kilowatt hours per kilogram nitrogen. Here for our RO and freeze crystallization at a 70% water removal, we're quite low. And then if we go to our 95% water removal, you can see that the advantages of using a hybrid RO EFC process compared to freeze crystallization alone means you can quite significantly reduce your energy requirements, removing that first big chunk of water. And then for alkaline dehydration and nitrification and distillation, we are still significantly lower. Important to remember, though, that the stats for energy consumption that I have for ROEFC and freeze crystallization are theoretic numbers, whereas the team at EVAC and SLU have actual energy consumption data, which could be the reason theirs are a bit higher than the theoretical. But yeah, that's what work we did on freezing our P for maximum water removal. So in conclusion, the model accurately predicted which salt would form first. We were able to experimentally show for the first time that salts form at the eutectic point in real urine. We were able to produce a more valuable fertilizer product by removing undesirable salts. And by using a hybrid RO-EFC process, we can reduce our energy requirements. Thanks so much, everyone. I'm not sure how to stop sharing.
Thank you very much, Caitlin. So now we'll take a pause for questions. So we had a presentation on production of vivianite from urine, another one on using an MBR with powdered activated charcoal, powdered activated carbon, and biochips for partial nitrification, the deactivation of urease using ultraviolet light, and then eutectic freeze concentration coupled with RO for volume reduction. So come on up, anyone who has a question on any of those topics. And how do we do the chat one? Do I?
Everything that's been asked in the chat has been answered.
Wow.
I'm not sure what's for.
Okay, there's a question of if it's possible to use vivianite as a fertilizer. And I guess I would add a question that others might be asking is, what is vivianite used for? It has value, was clearly stated in the presentation, but why does it have value? Why is it, what's it used for? And why is it not cheap and abundant if it's useful? Let's see, do we still have
Yeah, I'm still here.
Yes.
Could you please repeat the last part?
So I say again?
Could you please repeat the last part of your question?
Oh, sure. The question was what is vivianite used for? Why is it useful, and why is it expensive?
Okay, so it's, first of all, it's got multiple uses. I brought up 3, which are very common. The first is it can be used as a slow release fertilizer. That's for phosphorus and iron. And the second is it's been proven by researchers to be able to produce high value lithium iron phosphate that can be used as a feedstock for the production of lithium ion batteries. Then the third one is in the art industry. In the past, it was used as a paint pigment. So when artists want to validate if a certain paint work is actually the original, they could actually backdate based on the decay of the vivianite pigment in the paint to see that it's actually the original artwork based on the time of its painting. So those are just some of the uses, and because of that, those abundant uses, it draws that high market value. Does that answer the question?
Thank you. Yeah, Arthur.
So I have a question for Courtney and your team, kind of thinking about the Natnael's presentation about using UV to stabilize the urea. Do you think that there's any potential kind of co-use of these two ideas, to use urea to stabilize for UV, and then and how that would affect the eutectic freeze concentration process?
Obviously, any technique to stabilize the urine would be great. I'm sure if you had this like integrated, decentralized treatment process, I'm sure you could incorporate UV in it somewhere. But I know I've spoken to Natnael previously that they were looking at using the UV like within the toilet. I'm not yeah, I guess we would have to think about using it at the start of the process where the urine's still quite pale, because if you remember from the presentation, by the end of the concentration, I think it would be way too dark to use UV on the urine. But I think it's great that we have these spaces where we can network with these people, with other urine researchers, and think about how we can incorporate each other's work together.
Yeah, I guess as just a follow-up then, do you think
Yeah.
that, is there any reason to think that, I mean, obviously, so you mentioned you're taking the phosphorus out with the high pH treatment at the beginning.
Yes.
And if you weren't doing that, but there was, some other urea stabilizing
Yes.
process, how would having the phosphorus and still in the urine, do you have any idea whether that would affect that or not? The EFC process.
I'm actually not sure. I didn't think about modeling how, we obviously looked at modeling the urine without the phosphorus in it. So yeah, I'm not really sure if we'd maybe acidify it, like you say, or use some sort of other stabilization. I don't think it would change the EFC process necessarily. It might change which salt precipitates first.
Mm-hmm.
And then that might change, how you might have to have a multi-stage. So one of the things we looked at from the model is what we would have actually liked to have done is precipitate the urea in the EFC process and recover that in a nice pure form. That would have been the ideal scenario, but you had to freeze the urine to -30 degrees to do that. And so that didn't really seem feasible. But an interesting thought. I'll definitely pop it in the thermodynamic model and see how it affects the results.
Cool. Anyway, that's very exciting. Thank you so much for your work.
Thank you.
Okay, we have a couple of other questions in the chat, also for Caitlin, but I'll pose a question to Natnael first, so we can revolve some people around. The question is, if you succeed in a real urine situation of destroying or deactivating the urease, what happens after that when it's flowing through pipes or into a tank? Are you expecting that it would continue to be stabilized, or is there potential for bacteria in the pipes in the storage tank to produce more urease that would then hydrolyze the urine?
Good question. Like after the treatment, if it's going to pass through the pipe, and then if that pipeline is not sanitized, yes, probably there will be like urea hydrolysis by the bacteria, these bacteria. But what we are hoping is that, like, after receiving the fresh urine, we'll pass it through the UV treatment and then store it like very near. Or if you want to transport the urine, you will collect it while that receiving section has the treatment unit in treatment, and then you collect and then transport it to the central facility, where that facility also incorporate the UV. So that way you can minimize the chemical addition and also the buildup of like precipitates. So that's the whole idea behind it. But
Great.
Still, as you said, like the concern is also there. If the pipe is sanitized, not sanitized, there is a possibility.
Great, thank you. How are we doing? Can I take a couple more from the chat on time? Okay, great. We had a couple of questions about the eutectic freeze concentration. One of them is whether whether you've given consideration to what could be done with the water, and if you have any ideas how the water could be reused beneficially, and then also how you would scale up that freeze process for bigger volumes.
So the water, so yeah, you're removing some water in the reverse osmosis step, and then there would be the ice in the freeze crystallization step. So in both of those cases, there'll still be some contaminants, so I definitely don't think it will be potable water. But that's something definitely you could use for non-potable sources we were thinking something like on-site for cleaning or for watering gardens. You know, the problem is with water is it's expensive to transport and water is cheap. So even though we're in a water scarce country, to ship that water anywhere probably wouldn't make sense, but I'm sure we would be able to find use for it on site, wherever this decentralized urine treatment plant is. You know, maybe it's in the basement of a building, and then you would use that water within the building. And then the second question is scaling up the freeze crystallizers. So in a different context, another research group at our university who does some work on EFC, they actually built a plant, I believe somewhere in Joburg, a more scaled up version of the EFC plant, but to treat mining wastewater. So it's something that's been done before. You basically just size up the crystallizer. So I was working with a small 500 ml glass crystallizer, and they can get much bigger. So I'll see if I can find the article on that team's work and see if they've got some photos of the full scale EFC process that was used for mining wastewater.
Great, thank you. And we have one more question from in person. Andy.
Yeah, hi. My question's for Chibambila. I was wondering, to what extent do you think that partial nitrification of the urine might improve vivianite purity and yield, given that it would reduce the pH to 1 more in your operating conditions and have effects on organics removal for that?
Hi, thanks for your question. I'm not sure what effect the partial nitrification will have, but one thing we know for sure is once you reduce the pH below 6, you do tend to have substantial trade-offs in terms of yield and purity, because there's like a drastic change in how the solubility of the vivianite behaves. So when you take it to low pH values, you tend to have less yield, even though the purity might improve, but it might not be worth the effort. Then in terms of organic removal, we are still open to investigating that, and yeah, we're open to more ideas. Yeah, thanks.
Cool, thank you.
Great. So we will now move on to more presentations. We have 3 more to close out this section. The next one is from Dr. Pravina Gangaharan, and Dr. Pravina Gangaharan is an assistant professor in the Department of Civil Engineering at the Indian Institute of Technology, Palakkad, India. She's a recent recipient of Early Career Research Award, Women's Scientist Fellowship, the Bhagyalakshmi Krishna Iyengar Award, the Gandhian Young Technological Innovation Award, and the Gandhian Young Technological Innovation Award. Her research interests include bioelectrochemical systems for wastewater treatment, desalination, defluoridation of groundwater, nutrient recovery from urine, metal reduction and recovery, and electrochemical water or wastewater treatment. She's authored 6 research papers and in reputed international journals and 1 book chapter. So this is a recorded presentation, and here we go.
Hello everyone, myself Sangeeta B, research scholar, working under the mentorship of Dr. Pravina Gangadharan, Indian Institute of Technology, Palakkad. On behalf of our team, I'm very glad to present our work on magnesium fuel cells for simultaneous nutrient recovery and energy recovery in this rich earth summit. We thank you for giving us an opportunity to disseminate our work in this great forum. Growing human population poses a threat to food, water, and energy nexus. Studies report that NPK demand grow by 1.5, 2.2, and 2.4% respectively. We are all aware that finite resources are depleting at a faster rate, that there is a demand-supply mismatch. It is imperative to find an alternate resource to combat the future demand for fertilizers. So source-separated urine is the best option as it comprises 85% of total nitrogen, 50% of total phosphorus, and 55% of total potassium of the wastewater patternly constitute only 1% of its total volume. So to harness these nutrients, chemical precipitation and electrocoagulation are widely used techniques, wherein the chemical precipitation requires huge quantities of chemicals and electrocoagulation requires external energy supply which hinders it from scaling up. So magnesium air fuel cell is the recently emerging technology and gaining interest as it simultaneously leverages urine for both nutrients and energy. The electrode materials used for the construction of magnesium air fuel cells include the magnesium alloy A-31 as anode material and the carbon-based gas diffusion electrode as the cathode. The gas diffusion electrode comprises an hydrophilic catalyst layer, a stainless steel current collecting layer, and an hydrophobic gas diffusion layer that is facing the atmosphere. So this is our fabricated GD. We have characterized our gas diffusion layer for water contact angle, which was computed to be 117 degree, therefore demonstrating a hydrophobicity. Also, the surface morphology of the gas diffusion layer revealed the interlinked porous networks of the carbon particles formed by the PPFE linkages. It is worth noting that these gas diffusion electrodes demonstrate a triple phase interface that facilitates oxygen reduction at the cathode. So we will now look into the mechanism of nutrient recovery from source separated urine using a magnesium air fuel cell. At the anode, magnesium oxidation takes place spontaneously and magnesium ions are introduced into the urine as per this equation. Simultaneously at the cathode, oxygen from the atmosphere is diffused through the gas diffusion layer and reduced to hydroxide ions as per this equation. Meanwhile, urea hydrolysis also takes place and the magnesium ion starts reacting with the ammonium and phosphate ions to form struvite under optimum conditions such as pH, supersaturation, ionic strength, etc. So this slide presents the time post evolution of magnesium air fuel cell. First, we started with a single cell magnesium air fuel cell with a working volume of 250 milliliters. This demonstrated an open circuit voltage of around 1.6 volt and a power density of 4.7 watt per meter square. Later, we moved on to 4-cell magnesium air fuel cell for enhanced resource recovery, wherein each cell is having a working volume capacity of 750 milliliters and obtained a power density of around 6 watt per meter square. Currently, we are working on scaled up magnesium air fuel cell setup, say 50 numbers of individual units having a capacity of 100 ml to leverage the ionic strength of urine for power production. So these have a working capacity of around 100 ml when connected in parallel and series combinations. It can power around 36 LEDs in series as well as a smartphone battery. So we started exploring the effect of ammonia phosphate ratio of real source separated urine for struvite formation. We varied the ratios by mixing fresh and hydrolyzed urine in proportions to achieve the respective required ratios as presented in this table. We conducted the experiments in both closed circuit and open circuit conditions and achieved the phosphorus recovery efficiency as presented in this graph. So it is obvious that the high ammonia phosphate ratio achieved nearly 99% of phosphorus recovery at the end of the 24 hours, whereas the condition with low ammonia phosphate ratio, say fresh urine, it achieved only 20 to 40% within 24 hours. And the precipitate obtained from the condition number 3, that is having an ammonia phosphate ratio of 90:1, was confirmed to be struvite as per the XRD pattern. So this slide presents the electrochemical performance of the system under various experimental conditions. So this graph is presenting the temporal variation of the current efficiency of magnesium air fuel cells. A current efficiency greater than 100% denotes that the passivation layer has been formed. In case of condition number 3 and condition number 4, the current efficiency values are very stable and it lies well below 100% revealing there is no passivation. Whereas in the case of condition number 1 and condition number 2, the current efficiencies are way high than 100%, which reveals the formation of the passivation layer. So this current efficiency graph could be correlated with the anode potential of the systems also. So the more the negative the anode potential, the system would be more spontaneous. Here in case of the condition number 4, the anode potential seems to be towards a more negative side and it is more spontaneous, which means the magnesium ions are released into the solution spontaneously. So this is also confirmed with the physiochemical parameter or physiochemical variations also. Whereas if you take the condition of condition number 2 with the current efficiency greater than 100, the anode potential of the system lies towards a more positive side, revealing the less spontaneity. So this less spontaneity could be attributed to the resistance offered by the passivation layer formation. So the electrochemical performance are well correlated with the physiochemical parameters of magnesium as well as phosphate concentrations also. The major challenge we faced during the magnesium air fuel cell operation is the excessive magnesium oxidation, which preferentially combined with the bicarbonate ions that was released during the urea hydrolysis. So this phenomenon is further aggravated by the low phosphate ion concentration in the influent urine. So this is the ex-ante pattern of the precipitate that we recovered from the closed circuit conditions during the operation in magnesium air fuel cells. So this is well correlated with the ex-ante pattern of the nasty hornite, which is nothing but the magnesium carbonate. So now we are working on the solutions which is having experiments to understand the precipitation quality by varying the magnesium and bicarbonate ratio with other ions as well. So we are now working on to eliminate the interference of the bicarbonate ions in the precipitation of struvite. Moreover, we are also exploring the potential of magnesium air fuel cells for harnessing the ionic strength of urine. If you see here, 4 cells of magnesium air fuel cell are connected in parallel would power 36 LEDs in a row. And also, 50 numbers of individual MAFCs are connected in series and parallel combination would be powering a smartphone battery. We would like to acknowledge the financial support by the Science for Equity Empowerment and Development Division of Department of Science and Technology, Government of India. Once again, we thank the organizers for giving us the opportunity to present our work in this great forum for sanitation research.
Great, thank you very much for that. Unfortunately, this is not a presentation we can ask questions at because it's a pre-recorded and the presenter is not on Zoom. But if you have questions, you can relay them to us and we can pass them on. The next presenter is Dr. Sudeep Popat, who is an associate professor in the Department of Environmental Engineering and Earth Sciences at Clemson University. His research group focuses on biological and electrochemical technologies for resource recovery from domestic and industrial wastewater. Some of Dr. Popat's group's recent work includes using electrochemical technologies to enable N and P recovery from source-separated urine, developing electrocoagulation as a possible technology for primary treatment of animal processing wastewater, and expanding the understanding of anaerobic conversion of fats for anaerobic co-digestion applications for enhanced biogas recovery from municipal wastewater solids. And it looks like we are ready to go here, so please go ahead.
Perfect. Yeah, thank you so much. Thank you for this opportunity to talk about the work that we've been doing with source-separated urine. I want to point out, I think this is my 4th year presenting, and so it's great to be part of this community and be able to continue to share our work. Before I get into what I'm going to present today, I just wanted to acknowledge Phil Arvey, who is a PhD candidate in my lab, who did all of the research that I'm going to present about. And in fact, all of his PhD research is what I think I've presented over the last 4 years. He's very close to finishing up. So again, thanks to him for really doing all of the in-lab work that went into this research. So I wanted to very briefly first introduce what my group does. And so we have looked at urine processing, source-separated urine processing, and try to think about ways in which we can contribute with technologies that can make processing easier, more effective, and more efficient. And we've focused almost exclusively when it comes to source-separated urine on electrochemical technologies. And there are multiple places. This is a diagram that I've borrowed from the Research Institute, and there are multiple places where we think electrochemical technologies could fit in within this processing train. Collection, for example, maybe requires addition of some chemicals to stabilize urine. Treatment maybe requires addition of chemicals to remove or recover nitrogen or phosphorus. And so across all of these, our philosophy is that we can, instead of having to add chemicals directly into source-separated urine, where we would have to store chemicals and have some sort of replenishment over time, we could actually produce chemicals in situ using electrochemical reactions. And so that's what we've been focusing on last year, and maybe even I think the year before. I talked about our work on how we have generated hydrogen peroxide in situ in source-separated urine, with the idea that that peroxide acts as a urease inactivation system, and where we would then be able to keep urea in collected urine for later recovery. We actually, last year, what I presented was we've expanded this to applications where we do build in. I know the earlier presentation was about a magnesium electrode. So we've done there where we've combined our hydrogen peroxide cathodic production with anodic magnesium dissolution, which is a work that we've collaborated with Dylan Randall and Prithvi Simha, who I see are here. But today, what I'm going to talk about is a slightly different system, which is where if the urine has already been hydrolyzed, how do we recover ammonia from it? And so we've done a lot of work with what's called electrochemical ammonia stripping, where the idea is that you feed hydrolyzed urine to an electrochemical cell, as shown here. Typically, historically, in the few years of research that has focused on this, the urine is fed to the anode chamber of an electrochemical cell. The anode is where there's an oxidation reaction that occurs. In this case, the anode is where water gets oxidized to oxygen. But because you are doing that reaction where you are liberating electrons, you actually also have to have a positive ion that moves from the anode side to the cathode side. So if you have a cation exchange membrane, ammonium will selectively move because of higher concentration of ammonium as predominant cation in hydrolyzed urine. You would have that ammonium move to the cathode, where you are reducing water to hydrogen gas. And in doing so, you produce a base. And so here we are leveraging the use of that base to convert ammonium to ammonia that can selectively stripped out. And that's where the term electrochemical ammonia stripping comes in. And so the key here is ammonium moves through a membrane from the anode to the cathode, where it then gets converted to ammonia, which can be recovered. And there are multiple ways in which that ammonia could be recovered. You could have that gas go through a stripping column. You could do transmembrane chemisorption. You can use gas permeable membranes. There's a whole body of literature that has shown how the ammonia, once it's produced from the ammonium, could be recovered in an electrochemical system like this. And so we were really interested in this, and we were trying to understand, what are maybe some of the challenges that could occur in a process like this. One that came to our mind was that when we feed hydrolyzed urine to the anode of an electrochemical cell, while we are trying to oxidize water to produce oxygen and electrons so that ammonium will move across the membrane, we also have this risk of chloride in the hydrolyzed urine being oxidized to chlorine gas. And the reason for that is that the reduction potentials for both water oxidation to oxygen and chloride oxidation to chlorine are actually very similar. And because of that, we would expect there to be some chlorine production. And in fact, Will Tarpe, I think he did some work on this. This is some of the early work on this, which showed that you do produce chlorine with synthetic urine, at least, when it's fed to an electrochemical ammonia stripping system. And so we were interested in characterizing this problem further and maybe finding a solution. And so one of the solutions that we thought was, well, if you wanted to completely avoid chlorine, what could you potentially do here? And the answer, in fact, turned out to be pretty simple, is that could we just feed hydrolyzed urine to the cathode so that we feed some sort of salt solution to the anode, and we have some sodium move from that salt solution into the cathode chamber, which is where the urine is being fed. But by doing this, you isolate the chloride from the anode, right? So the chloride can only get oxidized, and so you don't want chloride to interact with the anode electrode. So in this case, by feeding the urine to the cathode only, you would be typically then avoiding any sort of chlorine production. And so we wanted to characterize how an anode-fed system for electrochemical ammonia stripping would work against a cathode-fed system for electrochemical ammonia stripping. And the idea here is, could we then characterize how well we remove and recover ammonia, as well as whether we avoid chlorine production in one versus the other, and what are some other downstream sort of issues with one versus the other feeding mechanism. And so what we've done is we've characterized ammonia removal and recovery from synthetic urine as well as real urine. I'm showing here results only from synthetic urine, where we are tracking total ammonium nitrogen with time. The key variable here is the current density. So the current density is the charge at a specific rate that you're applying in this system. So it's the rate at which you're moving electrons from the anode to the cathode. The important thing here is that that then fixes the rate of movement of any ions between the two electrodes, as well as the production of the acid or the base, right? So acid produced at the anode, base produced at the cathode. So essentially, by changing the current density, we are changing the rate of ion movement as well as the rate of production of hydroxide in the system. And so what was good to find here is that whether you feed the urine on the anode or the cathode, you get very similar removal and recovery of ammonia. And that was, in a way, expected. In one case, in the anode-fed, we are relying on transport through a membrane and then conversion, versus in the cathode, we are directly relying on hydroxide acting on the ammonium. But in either case, we get very similar rates of total ammonium nitrogen removal, which is what we would expect. So from a performance perspective of how well nitrogen is removed or recovered, either of the two mechanisms of operation, anode-fed or cathode-fed, don't seem to have a big impact on the system. But what we really saw is that we then tried to do experiments where on anode-fed systems especially, we're trying to measure chlorine that is produced. And what we wanted to do was actually compare both synthetic and real urine. In that earlier study that I mentioned, chlorine was detected in synthetic urine, but not in real urine. So this is when urine, again, hydrolyzed urine, synthetic or real, was fed to the anode chamber of an electrochemical ammonia stripping system. And again, showing here the three conditions, which are higher current densities from the lowest one that we start with. And again, higher current density here means faster reactions, faster transport of ions. And across all conditions, we detected chlorine in synthetic and real urine. We did have higher concentrations in synthetic urine than in real urine, probably because of the chloride concentration differences that we had between the synthetic and the real urine. But that verified that you can, in some cases here, for example, with real urine too, getting close to about 10, 15, 20 milligrams of chlorine, which is fairly high concentration of chlorine. And so we would want to avoid such a scenario where you're trying to recover nitrogen from hydrolyzed urine, but we ended up producing chlorine in the urine because there can be some downstream effects as well. What I would also like to point out is that when we feed the urine to the cathode, we still obviously try and measure chlorine on the cathode. We are not going to see any chlorine because chloride is just non-reactive under those cathodic conditions. And because we use a cation exchange membrane, no chloride moves over to the anode. And so we don't see any chlorine on the anode in cathode-fed systems as well. So we could not detect any chlorine in a cathode-fed system. So one of the issues that if you do anode-fed operation, one of the issues would be that the chlorine could form disinfection byproducts with organics that might be present in the hydrolyzed urine. And so we also, in our real urine-fed experiments, looked for disinfection byproducts when chlorine was also being actively produced. And so the ones that we actually found make sense. A lot of chlorinated disinfection byproducts, such as trichloromethane, dichloromethane, dichloroacetaldehyde. All of these we found in our higher current densities. And some of these concentrations were actually pretty high. So these are micrograms per liter. Some of these, that means we ended up, for example, for dichloroacetaldehyde, and for dichloromethane, at the highest current density, we ended up with that over a milligram per liter, which is, again, pretty stark and something that definitely would need to be avoided in an electrochemical ammonia stripping system. Again, no detection of any disinfection byproducts in a cathode-fed system because we just completely avoid production of chlorine in that system. Now, that does bring me to the question of, are there any downsides to cathode-fed operation? And so I didn't mention this, but I'm going to point out very specifically is that either of the two mechanisms, right? So if you do either anode-fed operation or cathode-fed operation, you will have to feed some sort of an electrolyte to the counter electrode. In an anode-fed system, you could feed any salt solution to the counter electrode and it's okay. In a cathode-fed system, because we are moving typically then sodium through a cation exchange membrane to the cathode, where the urine is going to be, the performance of the entire system will actually depend on the concentration of sodium. So performance in this case cannot be decoupled from the salt concentration on the anode. And then the question is, well, if you're trying to rely on a base production to strip off ammonia and you still need to add a salt at a sufficient concentration, you're still adding external chemicals rather than relying on in situ chemical feed, right? Which is what the whole idea with this system was. But we think we have a solution, which I think we are hoping to test out over the next year and hoping to present at the next Research Summit, which is that we can actually design a system where we can continue to feed urine to the cathode. We can continue to convert ammonium to ammonia, but then we have that high pH urine effluent actually go into the anode chamber. So we are not using an external sort of salt solution. Urine acts as both the catholyte and the anolyte. And the reason why this is important is that you want to feed it in a way where you are going to avoid chloride oxidation. So how do we get to not getting chloride being oxidized? We use a pair of membranes rather than a single membrane. So we use a cation exchange membrane and an anion exchange membrane. The anion exchange membrane facing towards the cathode, the cation exchange membrane facing towards the anode, so that chloride gets that's selectively removed as the anion from the urine from the cathode, and then sodium gets removed. And so again, no chloride makes it to the anode, and we have the center chamber, we collect a sodium chloride solution. This way, it can be a completely chemical addition-free system where the only chemicals added are the base and the acids that are produced at the anode and the cathode. I'm not going to show this today, but we've also done some analysis on how much energy requirement this typically ends up being. And again, it's significantly lower. Some of the current densities that I mentioned are per volume of urine. If we were to go to just how much power is needed per gram of or per kilogram of nitrogen that could be recovered, we are at 1/10 of how much energy is required to fix nitrogen into ammonia using the Haber-Bosch. So this does, from an economic standpoint, make a lot of sense. And the fact that the materials that we can use in the system, because we are at very low currents, we can actually make really cheap electrochemical cells in this way as well. And so with that, I'll leave with 3 take-home messages. That for electrochemical ammonia stripping, it does make sense to avoid issues with chlorine production of disinfection byproducts, to actually go with cathode-fed operation. And the reason is that cathode-fed operation gives you the same benefits in terms of nitrogen removal and recovery, except you don't have the issues such as the anode-fed operation, where you have substantial chlorine production, even with real urine, and then detectable levels of disinfection byproducts that you can then avoid in this particular system. And so with that, I'll end here and wait for questions after we are done with the session. Thank you.
Great, thank you so much. We'll now move to our last session of the day, not the day of our last presentation of this session, and I really appreciate that Dr. Jade Jiang is here who is actually Zooming from Sydney at, I believe it's 3 a.m. your time, Jade. So she's making quite an effort to be here with us. Yes, great. Yes, thanks for being with us, Jade. And so she also can probably answer any lingering questions people have from Weonjung Sun's talk earlier, because they're both at the University of Technology, Sydney, working on the membrane bioreactors with urine. So Dr. Jade Jiang is a postdoctoral research associate at the School of Civil and Environmental Engineering, Faculty of Engineering and Information Technology at University of Technology, Sydney, UTS. Currently, she's working with the ARC Research Hub for Nutrients in a Circular Economy, the ARC NICE Hub, utilizing ultrafiltration-based membrane bioreactor technology to achieve complete nutrient recovery and develop next-generation fertilizer from source-separated urine contributing to sustainability and the circular economy. And Jade, you can go ahead and share your screen and start your presentation when you're ready.
All right, so good evening. No, yeah, no, good morning. Everyone, can you guys hear me?
Yes.
Okay, cool.
Yes,
we
we can.
So
We can hear you, but you do seem to be not in presentation mode yet. While Jay's getting ready, I can just note that I was actually in Sydney as a guest of UTS Sydney for the ArcNice Hub Summit, and saw this bioreactor, or these set of bioreactors, and it's very exciting to me because it's another approach on the partial nitrification challenge that EVOG did pioneer years ago, and Photoinactivation does now, but this is with the membrane bioreactor instead of a moving bed bioreactor, and it's a different set of issues and another approach to the same problem, which is always exciting to see that.
right, so hi everyone, and welcome to my presentation. My name is Jade Jiang from University of Technology, Sydney. I'm going to talk about the potential nutrient recovery from salt-separated urine through hybrid membrane bioreactor and membrane capacitive deionization. Firstly, I want to talk. Why the screen is not? Yeah. So firstly, I will talk about the reason for using the hybrid MBR-MCDI technology to achieve the nutrient recovery from salt-separated urine for circular economy. Then we will look at the experimental design, and finally we will discuss the results and the conclusion of this work. Right. As mentioned by other speakers earlier, urine is enriched in nutrient in concentrated volume, making it an attractive stream for nutrient diversion and recovery. Biological nitrification, that's a two-step biological oxidation process, is also a promising technology to oxidize volatile ammonia into a stable and non-volatile nitrate form, where all other nutrients are preserved. The CDI operation is a two-step process as well. Absorption, where the ions are removed during the application of the voltage, and desorption, during which absorbed ions are released into the water. The proposed MBR-MCDI technology offers energy efficiency, affordability, ease of the operation, and eliminates the need for additional chemicals. The aim of this work, as mentioned earlier, is to investigate the nutrient recovery from the actual urine using a hybrid MBR-MCDI technology. The effects of different voltages on the absorption and desorption of ions was also studied. A pilot-scale gravity-driven nitrifying membrane bioreactor with 6-liter working volume was set up at the urinal room in the University of Technology, Sydney from our previous work. The MBR permit was pumped at 20 milliliter per minute and was used as a feed for the MCDI, so that nutrients such as ammonia, nitrate, and phosphate were recovered along with other ions. The total absorption and desorption time was 5 minutes for each cycle. A total of seven absorption and desorption batch cycles was conducted among 1, 1.5, and 2 volt operating voltages. Sorry? Can I continue?
Yes, please do. I'm not sure if you heard something, but yeah, just go ahead.
Yeah, I heard some people talking, so I was like, okay. Right, so this slide shows the variation of the TDS profile in the treated and concentrated urine solution at different cycles under different applied voltages. The effects of increased voltages on the TDS removal is evident, where high voltage application resulted in better TDS removal. For example, where the maximum TDS removal was 35% on the 1 volt application, it increased to 56 and 81% as the applied voltage increased to 1.5 and 2 volt.
Similar trend was observed in TDS concentration in the brine, as high reverse voltage lead to the better desorption and concentration. Overall, at the end of the 7th cycle, TDS in the brine increased from about 23% to 58% when the desorption voltage increased from -1 volt to -2 volt. So the different voltages were used to remove sodium, potassium, magnesium, calcium, and the ammonia in these slides. The removal efficiency increased as the voltage increased for sodium and potassium. Magnesium removal went up from 28% at 1 volt to 45% at 1.5 volt, but didn't increase further at 2 volt. Calcium removal increased from 54% to 87% at 1 volt to 1.5 volt, then dropped to 74% at 2 volt. Ammonia removal was 33% at 1 volt and 1.5 volt, but it increased to over 58% at 2 volt. So as for the cation recovery performance at the different voltages, similar to cation removal efficiencies, higher applied voltages also resulted in increased recovery from specific cations. Ammonia recovery was approximately 60% at both 1 volt and 1.5 volt, with a noticeable increase to over 76% at 2 volt. And as for the ammonia removal efficiency among different applied voltages, as expected, higher voltages lead to increase the removal rate for nitrate, phosphate, and chloride ions. Nitrate removal went up from 40% at 1 volt to 67% at 2 volt, and chloride removal increased from around 25% to about 88% as a voltage increased from 1 volt to 2 volt. This trend continued in the recovery of anions, where an increase in reverse applied voltage significantly enhanced their recovery. And in these slides, the energy demand for the removal and recovery of ammonia ranged from 3 to 11 kilowatt-hours per kilogram of ammonia across 3 different applied voltages. Similarly, for nitrate removal and recovery, the energy demand varied from 3.8 to 14.7 kilowatt-hour per kilogram of nitrate for the 3 different voltages. Optimizing the energy required for absorption and desorption in MCDI can be achieved by harvesting energy during the desorption stage. Given that the working principle of CDI is almost similar to a capacitor, the energy invested in absorption can be recovered. It also demonstrated that 47% to 80% of the energy invested in ion absorption can be recovered during the desorption stages to optimize the energy consumption. In conclusion, lower voltage resulted in lower removal and recovery efficiency and significant improvement in the performance at high absorption and high reverse voltage desorption. Overall, nitrate, phosphate, and ammonia removal were 66%, 49%, and 58% respectively, while recovery of nitrate, phosphate, and ammonia was around like 80%, 64%, and 76% in the concentrated brine. The energy demand for the recovery of ammonia was between 3 to 11 kilowatt-hour per kilogram of ammonia, and between 3.8 to 14.7 kilowatt-hour per kilogram of nitrate among 3 applied voltages. I'd like to acknowledge that this project is supported by Australian Research Council through the ARC Research Hub for Nutrient in a Circular Economy. Thank you.
Great, thank you so much. So now we can take questions for Sudeep Popat and for Jay Jiang about these 2 systems using electrochemical processes for nutrient removal and recovery. Any questions from the room? What do we have on Zoom? Anything unanswered?
Conversation with Sudeep, I think that all got answered.
Okay.
Abby had a question for like anyone in the group.
Okay.
Broadly.
Okay, so I can read it from here so everyone can hear it. This is from Abby Cohen, who is present. Is anyone aware of any techno-economic analysis taking into account projected scale on CapEx, OpEx, and end product value on the market for the furthest along valorization technologies. So that, I guess, could be for the panelists or anybody else. Okay. Any economic assessment of any of these? And this is for electrochemical, or is this for?
This is for like valorization technologies.
Oh, okay.
For producing an end product that has some known market value.
Okay.
So taking into account how much energy it would use, and like projected. I know most of these things are at the lab.
Right. Okay. Wrong way around.
Can't hear that part.
So thanks for all of the panelists. You've presented a lot of really interesting research. And I'm curious, as somebody who is impatient for like getting this stuff into the world, if people are aware of any analysis that's looked at I know going from bench scale to full scale is really hard to project what the energy use and the labor requirements and materials and all that will be. But if anybody has looked at things that have gotten to a scale where we could maybe put some values, projected values to those costs, and then compared side by side, all right, so this technology is going to require this much energy per kilogram of nitrogen, say, and the nitrogen product it produces is a urea-based product, which we know gets this value on the market. So we can evaluate, what makes the most sense to scale up right now. What's a promising approach to scale up right now? And I'm wondering if people have done that analysis or are familiar with people who have done that analysis or are interested in doing that analysis with me because it needs to be done.
I have thoughts on a couple of people who may have some of the pieces to that, but does anyone in the room or on Zoom have a complete answer, or maybe not a complete answer, but have a solid answer they want to share on that question?
I'll mention that at least for the technologies that we've worked with, we've done very rudimentary analysis, and we would be interested in partnering up to,
Great.
to get deeper into these analysis.
Great. What I was going to note is I was talking to Fabian yesterday, and you shared a paper with me that looked at energy usage of a variety of different concentration technologies. So that seems to be relevant. And someone earlier today, was it Courtney who shared a list of the cost of different fertilizers being largely based on the nitrogen content? So those seemed like two pieces to that puzzle.
And I know there's the
rough estimation.
Nancy Love LCA for city scale stuff,
which is
more on
environmental impacts,
right.
not economic costs.
But it would have energy use, I would presume.
Yes, energy use. Yeah.
So I guess we got to write that paper.
It's true. Talk to Abby about that paper and let's get it written. I had a couple of questions for both these presenters. How are we doing on time, Julia?
5 minutes.
5 minutes. Okay, great. So I had a question. Let's see. First for Jade, I wondered if you had an opinion on the potential for free chlorine to be created. Is that a risk with the capacitive system that you're working on, or is there a reason that is already handled?
Well, that's a good question. We haven't really looked at that one yet, but I think that's a good, that definitely that's gonna be a direction we're gonna investigate later on.
Okay, great, thank you. And Sudeep, I was wondering, as someone who's not well versed in how these systems work, I was a little bit confused in your last slide that had the two membranes. And if you're able to actually share your screen and go back to that, I wonder if others might be curious about this as well. I'm curious where the ammonia is actually going and how it's leaving the system and what happens next. It is the ammonia we're looking at, right? In terms of So
here there's multiple ways in which ammonia could be recovered, and that's kind of what I showed earlier. I think so. I maybe want to go up to my other screen, the other slide, where there's multiple approaches in which you can get ammonia out, right? So at this stage, ammonia partly would be dissolved, partly would be a gas. There's a gas that's being produced at the cathode, so you have bubbles of gas coming out, which the output of this, if we collect the gas and want to do something further with it, is going to be a mixture of hydrogen and ammonia, but you can separate those out. But there can be other ways in which the ammonia could be removed as well. So there are, as I pointed out earlier, there are multiple approaches that many groups have already tried. I know, there's been some work in Netherlands with that, and I know, I think Ghent University also, they've done some work on this. So the post conversion of ammonia, I think there's multiple approaches. When we talk about, we've done some preliminary analysis on cost that's excluding what it takes to separate out the gas. But then you could have, ammonia recovered and maybe redissolved into an acid so that you have an ammonium, solution. So there's multiple approaches. This is just a selective way, I think, of taking out ammonium by applying current. Now, one of the things that I mentioned is that, well, with this modification, we are technically then also getting out sodium and chloride from the urine as well.
Great, thank you. So yeah, coming out as a gas, I missed that part. So thanks for clarifying. Okay, well, I think that wraps it up for questions in the room, and we're on time. So we'll conclude here. Thank you to all the presenters from this session. We appreciate you sharing your findings with us.
Thank you. Yes, thank you all. So we're going to take another break before our next panel. We'll convene back here at 11:30. If folks on Zoom want to go get your water and take care of your nutrients in and out. And we'll meet back here at 11:30 for the first part of a two-part panel on using urine as a fertilizer in agriculture. And we'll hear a few examples on that. So that'll be back here at 11:30. See you all then.